Welcome to the deep dive. You've likely seen the incredible buzz around AI lately, especially with large language models like GPT-4. They can write, code, even generate images with astounding fluency, and they've truly captured everyone's attention. But for all their impressive capabilities, it really makes you wonder, are these systems truly intelligent in a comprehensive human-like sense? Or is there something fundamental still missing from this current paradigm?
That's a really crucial question. Despite these significant leaps, many researchers argue that these current AI technologies are really just, well, initial steps. They propose that the next fundamental step in the pursuit of artificial general intelligence, or AGI, is something called embodied AI, or EAI. And this concept, it stands in stark contrast to the existing AI methodologies we've become accustomed to, particularly those large language models.
Right, embodied AI. So today our mission is to unpack what that actually is, why researchers believe it's so crucial for unlocking true intelligence, how it fundamentally differs from the AI we're used to interacting with, and the significant challenges that lie on this path. It's going to be a fascinating exploration. Okay, so embodied AI is the phrase, but what does it truly mean to have AI embodied in the real world? What are we talking about here?
Okay, so at its core, embodied AI refers to AI agents that are bound to observe, interact with, and learn from the real world, including humans, in a continuous and dynamic manner. So forget AI locked in a server room somewhere.
Mm.
This is about intelligence that lives in the world, that touches it, sees it, learns directly from its experiences, much like, well, like a human or an animal does. It's a concept deeply rooted in something called embodied cognition, a perspective that posits this profound coupling between the mind and the body. It actively challenges that traditional Cartesian dualism, the whole mind-body separation idea. And this paradigm, it really distinguishes itself from classical models of static learning. Instead of just passively observing mountains of data, these EAI agents actually act on their environment and learn directly from the reactions they get back.
Okay, and this is where it differs so clearly from current large language models, right? They're often described as static internet AI or
Yeah,
IAI
exactly.
because for all their incredible outputs, they can't really evolve with time or real-world experience, can they? They leverage these massive data sets, but they lack what the research describes as the ability to properly care about the truth, which sounds a bit philosophical, but means they can't dynamically adjust their knowledge or actively search for valuable new information based on real-world feedback. Is that right?
Precisely. And you see two primary manifestations of this shortfall in LLMs. First, there's the difficulty in effectively aligning them with human values and intentions.
Mhm.
Second, they have this tendency to generate information that sounds perfectly plausible but is completely inaccurate, what we often call confabulation, or, basically making things up that sound right.
Hallucinations.
Yeah, exactly. And while current mitigation strategies like fine-tuning or prompt engineering are valuable, they only address superficial aspects. They don't tackle the core issue, this inherent lack of a deeper, grounded sense of care, as the paper puts it.
Okay, here's where it gets really interesting, I think. The paper we're diving into argues that LLMs are only initial steps toward truly intelligent agents. They're perhaps analogous to just an aspect of the mind's reasoning function,
It's this one part, yeah.
but they fundamentally miss the perceptive and action-oriented dimensions of intelligence. And crucially, they lack that vital ability to dynamically update their understanding or beliefs based on new real-world experiences.
That's exactly right. For true understanding to be achieved, encompassing not only propositional truth, but also the value of propositions that guide us how to act, it's believed that it can only happen through EAI agents that actually live in the world and learn by interacting with it, not just processing text.
So to understand why this interaction is so vital, let's talk about a fascinating real-world example, the Heldenheim carousel experiment with kittens. Can you describe that a bit?
Sure. This was a classic study, really foundational. They had two kittens. One kitten could actively walk around and control the movement of this little carousel it was in.
Okay.
The other kitten was in a similar gondola, seeing basically the same things, but it was moved passively. It couldn't control the movement itself.
So identical visual input, essentially.
Pretty much identical visual input, yes. But what's striking is that only the actively interacting kitten, the one moving itself, developed normal visual abilities like depth perception. The passive one did not, despite seeing the same things.
Wow, that's really telling.
It absolutely is. This seminal experiment powerfully underscores the vital role of embodied interaction in shaping cognitive abilities. It reinforces the observation that all known forms of intelligence, including our own, are inherently embodied. It suggests that this embodied approach, it's a really solid foundation for cognitive learning. It might even be necessary.
So what does this all mean for us, the listener? It means humans learn by seeing, moving, interacting with the world, and speaking with others. We learn by collecting sequential experiences, not just passive observation of shuffled and randomized data like an LLM might get trained on. Our intelligence is built on this dynamic engagement.
Exactly. And this leads us nicely to the concept of affordances, which is
Mm.
basically what fill our world with meaning.
Of course.
Yeah, affordances. Embodiment is considered a prerequisite for learning about affordances. These arise from the dynamic interplay between an agent's perception, its goals, its abilities, and the characteristics of objects and contexts in its environment. So, for example, a chair affords sitting, but only if you perceive it correctly, have the goal to sit, and have the physical ability to do so. A doorknob affords turning.
Ah, I see. It's about the potential for interaction based on the object and the agent.
Precisely. This concept is fundamental for agents that can truly give meaning to their own world, rather than just processing abstract symbols fed to them.
Okay, so if embodiment is key, how do we actually start to build such intelligent systems? What does the blueprint look like?
Well, the theoretical framework for embodied AI draws heavily on cognitive architectures. These are frameworks that cognitive scientists have designed over decades to try and model the human mind, its different functional parts. And these frameworks typically identify four essential components for an EAI system. First, there's perception, the agent's ability to sense its environment.
Right, seeing, hearing.
Seeing, hearing, touching. But it's important to clarify, this doesn't necessarily require vision like ours. It could be implemented using any physical sense, like chemical or electric sensing, like you see in some organisms.
Okay.
Second is action, the ability to interact with and change its environment. And we can distinguish between reactive actions, sort of like human reflexes, for self-preservation.
Like pulling your hand from a hot stove.
Exactly. And then goal-directed actions, which involve strategic planning, high-level objectives, often using what's called a world model to predict the consequences of actions before taking them.
Makes sense. Then there's memory.
Third, yes, memory, the capacity to retain past experiences. And this has various dimensions like duration, short-term, long-term, or nature, like procedural memory, how to do things, or episodic memory-specific past events. Now, memory can be implicitly encoded in the AI's core structure, like in the weights of a neural network, or it can be explicit, like how some LLMs use something called retrieval augmented generation, or RAG.
RAG. Right, I've heard of that. It's like giving the AI access to a library.
Sort of, yeah. It helps them access and look up information in a vast knowledge base, almost like having an external library to consult for long-term memory or specific facts.
Okay, perception, action, memory. What's the fourth?
And finally, perhaps the most defining trait is learning. The ability of intelligent agents to integrate experiences to form new knowledge and abilities, and crucially, continual learning is key here for adapting over time.
Not just learning once and being done.
Exactly, adapting to a changing world. And this is where simulators become vital tools. They allow for this dynamic, interactive evolution, letting the AI learn by trial and error in a safe, simulated environment before, hopefully, going into the real world.
Okay, building truly embodied AI sounds incredibly promising, like we're finally maybe heading towards more general intelligence, but it also sounds incredibly difficult. What are some of the biggest hurdles and challenges we face?
Oh, there are significant challenges. You're absolutely right. First, we need basically a new learning theory for embodied AI. Classical supervised learning, where you just show it labeled examples, is insufficient for this dynamic, interactive nature of data, where the agent's own actions continuously reshape its learning environment.
The data keeps changing because the agent is changing it.
Precisely. Second, there's the pervasive challenge of noise and uncertainty in the real world. Things aren't clean and perfect like in a data set. This can drastically affect an EAI agent's perception and decision-making. Then there's the point about simulators, which you mentioned. They are fundamental for progress, kind of like data sets are for traditional AI. However, we face the reality gap.
Ah, yes, the sim-to-real problem.
Exactly, the difference between simulated conditions and real-world deployment. This often leads to models that look great in simulation but then fail, sometimes badly in practice. And that gap remains a largely unresolved issue.
Okay, what else?
Another major challenge is generalization. An EAI agent acting in the real world will inevitably encounter situations it wasn't explicitly trained on. Imagine a service robot in someone's house encountering a completely novel object.
Right. It can't just freeze.
It needs the ability to assess its own uncertainty, to know what it doesn't know, and avoid overconfidence, which is a really common shortcoming of current LLMs, right? They often state wrong things very confidently.
Definitely.
So the ability to perhaps seek human assistance when uncertain, the paper suggests, similarly to how infants ask for help, could be essential.
That's a really interesting idea. Humility in AI.
Kind of, yeah. And finally, we absolutely must confront hardware limitations. Current AI tech largely depends on these powerful, energy-hungry graphics processing unit GPU clusters.
Right, the big server farms.
Exactly. But those aren't really ideal for EAI's needs, especially if you want robots operating untethered for long periods. There's a clear call for energy-efficient, neuromorphic, brain-inspired hardware,
Yeah.
essentially. Computers built to mimic the brain's own highly efficient structure and processing style. That's a huge engineering challenge.
That's a crucial point about the limitations of LLMs, the whole caring about truth thing. But I've heard some argue that maybe with enough data, enough scale, enough computational power, LLMs could eventually bridge this gap, even without a physical body. What's your take on that counterargument? Is there something fundamental embodiment provides that scale alone cannot?
That's a great question, and it really gets to the heart of the debate. While scaling LLMs has yielded incredibly impressive results, just look at the latest models. The argument from the embodied AI perspective is that there's an inherent difference, a qualitative difference, not just quantitative. Meaning, you can give an LLM every book ever written, every website, all the text and images in the world, but it won't ever know what it feels like to pick up a book, to physically turn a page, or what the texture of the paper signifies, or the heft of it.
The grounding is missing.
Exactly. That direct, continuous interaction with the physical world, the cause and effect, the sensory feedback loop it provides, that's what researchers in this camp believe is crucial for true dynamic understanding and for the ability to actually value truth based on successful interaction with the world, not just statistically correlating symbols. Scale might improve mimicry, but maybe not achieve genuine understanding without that grounding.
Okay, that makes sense. It's a different kind of knowing. So this raises another important question then.
Yeah.
If we're looking to human babies for inspiration, how precisely do human brains learn so differently from current AI systems? You touched on it, but let's dig in.
Yeah, it's a fundamental difference in mechanism. Current artificial neural networks largely use a process called backpropagation. Basically, it adjusts the model's internal parameters, its connections, to reduce the error on the training data. But it often requires training hundreds of times, showing it the same information over and over again to learn effectively.
Repetition,
A
repetition.
lot of repetition. Now, contrast that with the biological brain, which demonstrates, frankly, a clear superiority in certain aspects. Humans can often learn new information by just seeing it or experiencing it once, and crucially, we can learn new things while maintaining our existing knowledge.
That's a big one.
It's huge because new learning in artificial neural networks often interferes with existing knowledge and degrades it rapidly. This is a well-known problem called catastrophic forgetting. You teach it something new and it forgets something old.
Okay, can you give us an example to make that clear? The paper used one with a bear, right?
Yes, the bear fishing for salmon. It's a good illustration. Imagine a bear has learned that if it sees the river, hears the rushing water, and smells salmon, then salmon are likely there to be caught. That's its learned pattern.
Okay, standard bear knowledge.
Right. But now imagine one day the bear arrives at the river with, say, a temporarily damaged ear, maybe an infection, so it can't hear the river very well that day. Now, in a typical artificial neural network trained with backpropagation, this lack of the expected sound input might cause the learning algorithm to significantly alter many internal connections. It might weaken the link between the smell of salmon and the presence of salmon simply because the hearing part of the pattern is missing. The whole pattern gets disrupted.
So because it can't hear, it might forget that the smell still means fish.
Potentially, yes, or the connection becomes much weaker. The learning process interferes. But in the animal brain, the bear still smells the salmon. The lack of sound doesn't catastrophically overwrite the knowledge that the smell is a very strong indicator. The bear still knows salmon are likely there for catching. That ability to isolate and update relevant knowledge without wrecking everything else is a huge difference.
That makes the concept of catastrophic forgetting really clear. So how does the brain avoid that?
Well, the proposed principle behind this in the human brain is something called prospective configuration. Think of it like our brain quickly getting a lay of the land or a rough sketch of a new situation before it tries to fill in all the fine details or make permanent changes.
Pre-organizing.
Sort of, yeah. It first settles the activity of neurons into an optimal, balanced configuration before adjusting the synaptic connections, the strengths between neurons. This efficient feature helps reduce that interference. It preserves existing knowledge, and it significantly speeds up learning because it's not constantly readjusting everything based on every tiny input variation.
Wow. Okay, so why don't we just build AI like that?
Well, there's the rub. Simulating this prospective configuration on our current computers, which are based on von Neumann architecture, is computationally very slow and inefficient. They operate fundamentally differently from biological brains, which are massively parallel and work with spikes in timing in a way our current hardware doesn't easily replicate.
So it comes back to hardware again.
It often does. This reiterates the need for potentially a new type of computer or dedicated brain-inspired hardware, like neuromorphic chips, that can more efficiently mimic these biological processes.
Okay, so given all these challenges, the theory, the hardware, what are the early steps we're seeing towards this embodied future? Are scientists actually building AI that learns more like a human baby, even in simulations?
Yes, absolutely. There are some fascinating early stats, sort of proofs of concept. One really notable example is BabyX. This is an interactive, quite lifelike virtual infant created way back in 2013 by Mark Sager and his team.
BabyX, I think I've seen videos of that. It's quite striking.
It is. Its virtual brain is modeled with a detailed likeness to the structure of the human brain, using an operating system they developed called brain language. And interestingly, it uses stimulated neurochemical reactions, essentially simulated versions of brain chemicals like dopamine or serotonin, to influence how it decides to react to things.
So it's not just code, it's simulating the brain's chemistry too.
To a degree, yes. And BabyX uses computer cameras for seeing and microphones to listen. AI algorithms then help it learn and interpret these inputs. It can learn to recognize objects, react to stimuli, even learn to read simple words over time, and it expresses its internal mood through remarkably realistic facial expressions, like smiling or looking curious.
So BabyX, by mimicking these basic human learning mechanisms and reacting to its, well, virtual environment, it provided a critical early proof of concept, right? That some core elements of embodied interactive intelligence can be simulated.
Exactly. It paved the way for thinking about how more sophisticated systems could learn from genuine interaction, even if simulated initially. Another really compelling example is PLATO AI. PLATO, yeah. It stands for Physics Learning Through Auto-Encoding and Tracking Objects. This AI was explicitly inspired by research on how babies learn intuitive physics.
Intuitive physics, like knowing objects don't just disappear.
Precisely. It was trained with specifically designed coded videos representing the basic physics concepts infants seem to grasp very early on, things like object permanence, objects still exist even when hidden, solidity, objects don't pass through each other, continuity, objects move along connected paths, and so on.
Okay, so they showed videos demonstrating these basic rules of the physical world. What happened?
Well, the really cool part was Plato's success. After training, when they showed it videos of impossible scenarios, things that violated the physical principles it had learned, like an object magically disappearing or passing through another solid object, Plato expressed surprise.
Surprise.
Mm.
How does an AI express surprise?
It's the AI equivalent of what researchers call violation of expectation signals in infant studies. Basically, its internal model registered a strong mismatch between what it expected to happen based on its learned rules and what actually happened in the video. And remarkably, this happened after relatively short training periods, sometimes as little as 28 hours of video.
28 hours. That's
Well,
incredibly fast compared to training huge models.
it is quite efficient for learning these core concepts, yeah. But it's important to acknowledge Plato's limitations, too. The researchers noted it's not quite up to the level of a 3-month-old baby yet.
Okay, still early days.
Still early days. For instance, it showed less surprise if there weren't clear objects present, or if the testing scenarios were too similar to the training ones. Also, the videos included some extra data to help it recognize objects in 3 dimensions more easily. So it reminds us that some built-in knowledge, or perhaps carefully structured input, is still required. It wasn't learning completely from scratch in a totally unstructured way.
These examples are truly fascinating, though, aren't they? BabyX and Plato. For me, they really underscore that this isn't just abstract theory anymore. They're actual proof of concept demonstrations that at least some central concepts in intuitive physics can be acquired through visual learning, through interaction, even simulated. What's the biggest takeaway for you from seeing these early attempts?
For me, I think it's the potential for a deeper understanding, not just of how to build better AI, but maybe understanding the human mind itself. If we can successfully replicate elements of how a baby learns something as fundamental as physics, it gives us incredible insight into our own cognitive development. What needs to be built in, what can be learned, how interaction shapes it.
Yeah, like a mirror to ourselves.
Yep. Exactly. And of course, as with any groundbreaking AI development like this, there's always a public discussion that follows. With really varied perspectives, you immediately see questions popping up about whether AI can truly think in a human sense, or philosophical debates, or even practical ones about whether raising AI like children in rich environments is the only way forward to achieve AGI. These early experiments are definitely fueling those broader conversations.
Okay, we've gone on quite the deep dive today into embodied AI, a really fascinating shift, I think, in the pursuit of artificial general intelligence, one that prioritizes interaction, experience, and grounding in the world over just static data processing.
Yeah, and this approach really suggests that the next frontier in intelligence might not be about simply scaling up our existing models bigger and bigger, although that's still happening, of course, but it might be more about designing AI that can truly experience, adapt, and grow within a dynamic environment. AI that's continually learning from its world and evolving, much more like a living being does rather than a static program.
It truly makes you wonder, doesn't it? If being in the world and experiencing it firsthand with all the messiness and interaction that entails is fundamental to genuine intelligence, what does that imply for the future of AI? And maybe even for our own human understanding of what it means to truly know and interact with the world around us. Something to think about.